Hello everyone. Today I'll be presenting on 316L stainless steel and its processing structure and property relationships in additive manufacturing. In this presentation, I'll discuss how manufacturing parameters affect the microstructure of 316L stainless steel and how those microstructure changes influence its mechanical properties and overall performance. Let's begin with an introduction to additive manufacturing in 316L stainless steel. Before focusing on 316L, I want to briefly explain the common features shared by the four structural materials in our topic. 316L stainless steel, Inconel 625, copper alloy, and titanium 64 alloy. Although their compositions are different, they all have several common characteristics. First, they must maintain high structural reliability because they are often used in aerospace, energy, or advanced engineering applications. Second, their properties are highly sensitive to microstructure, meaning that small changes in grain size or phase distribution can strongly affect the strength and toughness. Third, they are all strongly influenced by processing conditions, especially thermal histories, during additive manufacturing. That is why all four materials are frequently studied under AM conditions. Now, focusing on 316L stainless steel, one of its key advantages is its low carbon content. The L stands for low carbon, meaning that the carbon content is limited to 0.03% compared with 0.08% in standard 316 stainless steel. This lower carbon content improves weldability and helps maintain corrosion resistance. In addition, 316L contains chromium, nickel, and molybdenum, which contribute to its excellent corrosion resistance and mechanical performance. As a result, 316L is widely used in demanding environments where both strength and durability are important. In additive manufacturing, rapid solidification creates a refined microstructure that can further improve strength. For these reasons, 316L has become one of the most widely used materials in metal additive manufacturing. 316L stainless steel mainly has an FCC austenitic crystal structure, which means face-centered cubic. In this unit cell, atoms are located at the corners and the centers of each face. FCC is important because it contains 12 slip systems, allowing atoms to move more easily during deformation. That is why 316L shows excellent ductility and toughness. Another result of this austenitic FCC structure is that 316L remains non-magnetic in the anode condition. This iron chromium nickel phase diagram helps us understand the phase stability of 316L stainless steel. First, gamma austenite is the dominant phase in 316L stainless steel and remains stable at room temperature. However, under significant strain or plastic deformation, some austenite may transform into martensite, which is a harder phase. In addition, prolonged heating can lead to the formation of sigma phase, which tends to reduce ductility. Thermal exposure may also promote the formation of delta ferrite and carbide precipitation, both of which can influence phase stability and material properties. Therefore, although several phases can form under special conditions, gamma austenite remains the primary phase in 316L and is mainly responsible for its desirable properties. This slide shows processing during laser powder bed fusion, one common AM method for 316L. A laser melts powder layer by layer to form the final part. Three important processing parameters are laser power, scanning speed, and cooling rate. Inside the melting pool, there is a strong fluid flow caused by Marangoni effect, which redistributes heat and molten metal. Because cooling is extremely fast, solidification happens rapidly. After rapid solidification, LPBF process 316L develops a characteristic cellular microstructure. In this image, the dashed lines outline the cellular subgrain structure, also known as dislocation cells. This structure formed because cooling rate during LPBF is extremely high. As a result, a large number of dislocations are retained within the material, creating a high dislocation density. This high dislocation density strengthens the material by making plastic deformations more difficult. Therefore, the unique microstructure produced by LPBF is one of the main reasons why additive manufacture 316L can exhibit excellent mechanical properties. Although additive manufacturing offers many advantages, several defects can still occur in LPBF produced 316L stainless steel. First, lack of fusion pores may form when the laser energy is too low, preventing complete melting between adjacent tracks or layers. On the other hand, excessive laser power can create keyhole porosity, where vaporization causes unstable melt pool behavior and trapped voids. Another important issue is residual stress, which develops due to rapid heating and cooling cycles and may lead to cracking or part distortion. Finally, surface roughness can reduce fatigue performance because surface irregularities may act as stress concentration sites. The image on the right shows a partially melted powder particle, which is another common surface-related defect in metal additive manufacturing. Therefore, careful controls of process parameters is essential for minimizing defects and achieving high-quality components. Heat treatment is commonly used after additive manufacturing to optimize the microstructure and properties of 316L stainless steel. First, stress relief treatment reduces the residual stress generated during the printing process. Second, annealing causes the cellular subgrain structure to coarsen, which may slightly reduce the stress but improve the microstructural uniformity. Third, solution treatment helps stabilize the austenitic phase and improves the phase stability. Overall, heat treatment is important because it helps balance stress, ductility, and structural stability, resulting in more reliable material performance. Due to its excellent corrosion resistance, good mechanical properties, and compatibility with additive manufacturing, 316L stainless steel is used in a wide range of applications. In the biomedical field, it is commonly used for implants because of its corrosion resistance and biocompatibility. In aerospace, it can be used for brackets and lightweight structural components. It is also widely used in chemical industry, where corrosion resistance is especially important. In addition, additive manufacturing enables the production of heat exchangers with complex internal channels that would be difficult to manufacture using the conventional methods. These applications demonstrate the versatility of 316L in additive manufacturing. Finally, these structural features determine the final properties. First, fine microstructure increase the strength. Second, FCC austenitic phase preserve ductility. Third, corrosion resistance comes from the passive chromium oxide film on the surface. When chromium reacts with oxygen, it forms thin protective layer, and this layer can self-heal if damaged, which is why stainless steel has strong corrosion resistance. This table compares LPBF manufactured 316L with conventionally manufactured 316L. Overall, LPBF 316L offers a higher yield strength, better corrosion resistance, and significantly greater design flexibility. The improved strength mainly comes from the fine cellular microstructure and high dislocation density created during the rapid solidification. In addition, additive manufacturing enables the production of complex geometries that are difficult or impossible to achieve through conventional manufacturing method. However, LPBF also have some limitations. The production speed is generally lower, and the residual stress tend to be higher. The ductility is slightly reduced compared with conventional manufactured 316L. Therefore, LPBF provides an excellent performance and design freedom, but process optimization and post-processing are often required to achieve the best balance of properties. The performance of LPBF depends strongly on several processing parameters, including laser power, scanning speed, and scanning strategy. These parameters are often combined into quantity called volumetric energy density, shown in the left. VED describes how much laser energy is delivered to a unit volume of material. In general, increasing laser power increases the productivity, but excessive power may introduce defects such as hot crackings. As shown in the table, high-power systems can achieve much higher build rates than standard systems, but process control becomes more challenging. In addition, scanning strategies such as island scanning, 67-degree layer rotation, are commonly used to reduce residual stress and improve building quality. Therefore, optimizing these parameters is essential for balancing productivity, microstructure, and final material properties. One of the most important concepts of LPBF is the process window, which represents the range of parameters that produce high-quality parts. As shown in the figure, both laser powder and scan speed influence the energy delivered to the material. When the energy input is too low, the powder does not melt completely, leading to lack of fusion pores, bonding defects, and incomplete melting. On the other hand, the energy input is too high. Excessive heating can cause keyhole porosity, evaporations, and unstable melt pool behavior. Therefore, the goal is to operate within the optimized process window, where defects are minimized and part density is maximized. For 316L stainless steel, studies have shown that a power range of approximately 500 to 1,000 watts often provide a good balance between the productivity and material quality. One of the unique features of LPBF produced 316L is its three-scale microstructure, ranging from the macro scale to nanoscale. At macro scale, columnar grains grow along the build directions due to epitaxial growth, creating a strong crystallographic texture. At microscale, rapid solidification produces cellular subgrains networks. These cell boundaries contain a high density of dislocations and provide a fast chromium diffusion path. At nanoscale, small silicon aluminum manganese oxide inclusions can be observed. Unlike conventionally manufactured 316L, LPBF 316L typically contains few or no manganese sulfide inclusions. Together, these macro, micro, and nanoscale features contribute to the strength, corrosion resistance, and overall performance of the material. One of the major challenges in LPBF is residual stress. Residual stress is mainly caused by temperature gradient mechanism, or TGM, and by the thermal contraction during the rapid cooling. Because the material experiences repeated heating and cooling cycles, significant internal stresses can develop, sometimes approaching the material's yield strength. As shown in the figure, these stresses are generated around the melt port during the laser scanning. Excessive residual stress can lead to part distortion, reduced fatigue life, and even crack initiation. Therefore, post-build heat treatment is commonly used to relieve the residual stress and improve the dimensional stability. Heat treatment can have both beneficial and harmful effects on stainless steel microstructures. At around 400 degrees Celsius, recovery occurs with minimal microstructure change. The as-built structure is largely preserved, while some residual stress is relieved. However, the temperature range between 650 and 8 degrees Celsius is often considered the sigma phase danger zone. In this range, the brittle iron chromium intermetallic compounds called sigma phase may precipitate, especially around the grain boundaries. The formation of sigma phase can significantly reduce the ductility and negatively affect the material performance. Therefore, prolonged exposure within this temperature range is generally avoided during the heat treatment. Different heat treatment temperatures produce different effects on LPBF 316L. At 400 degrees Celsius, recovery occurs with minimal microstructure change. Although only about 24% of the residual stress is relieved, the risk of mechanical failure remains low. At 650 to 800 degrees Celsius, homogenization provides greater stress relief, but this temperature range overlaps with the sigma phase formation region, which may lead to embrittlement. At 11 degrees Celsius, solution aniline removes the most residual stress and causes complete recrystallization. However, it can also soften the material and reduce the strength. Therefore, the choice of heat treatment temperature depends on whether the priority is preserving as-built microstructure, maximizing stress relief, or balancing the mechanical properties. Solution aniline provides the highest level of stress relief among the heat treatment method we discussed. At around 1100 degrees Celsius, nearly 90% of the residual stress can be removed. It also dissolved the sigma phase and transformed the grain structure from columnar grains to more aqueous grains. However, there is a trade-off. Some of the microstructure features that make LPBF 316L strong begin to disappear during heat treatment. The nanoscale inclusions become larger, and cellular subgrain structure is largely lost. As a result, the material became softer and its strength decreases. Interestingly, studies have also reported a reduction in ductility compared with as-built condition. This is mainly because the inclusion coarsening and loss of subgrain strengthening reduce some of the benefits created during LPBF process. So, while solution aniline is excellent for stress relief, it does not always provide its best overall mechanical performance. This slide highlights an important idea. Yield strength and ductility are controlled by different mechanisms. First, yield strength is mainly controlled by the microstructure. In LPBF 316L, the rapid solidification process creates columnar grains, multiple boundaries, and a strong crystallographic texture. This feature makes dislocation movement more difficult and therefore increase the yield strength. However, ductility and failure behavior are influenced more by defects than by microstructure. As shown in the SEM image, defects such as porosity, unmelted powder particles, and lack of fusion defects can act as stress contractions. These defects often become the starting points of crack initiation and fracture. Therefore, improving strength alone is not enough. To achieve the best performance, we must optimize both microstructure and the density of the material by minimizing the defect. This slide compares the fatigue performance of LPBF 316L and conventionally manufactured 316L. In air, both materials showed very similar fatigue strengths at approximately 475 megapascals. However, the difference became significant in corrosive environments, such as 3.5% sodium chloride solution, which simulates seawater. Under these conditions, LPBF 316L demonstrates substantially better fatigue performance. The reason is that corrosion pits often act as initial sites for fatigue cracks. Because LPBF 316L generally has better pitting corrosion resistance, crack initiation is delayed and fatigue life is extended. As a result, LPBF 316L is particularly attractive for marine, chemical, and other corrosion-sensitive applications. To conclude, LPBF 316L achieved its unique properties through hierarchical microstructure that spans multiple length scales. Columnar grains, cellular subgrains, and nano-sized inclusions together contribute to its excellent strength and corrosion resistance. However, processing parameters must be carefully optimized. Increasing laser powder can improve productivity, but excessive energy input may also introduce defects such as hot cracking. Therefore, a power range of roughly 500 to 1000 watts often provides a good balance between build rates and material quality. Heat treatment is another important consideration. A recovery treatment at around 400 degrees Celsius can relieve stress while preserve the as-built microstructure. In contrast, temperature between 65 650 and 800 degrees Celsius should generally be avoided because sigma phase formation can reduce ductility. If maximum stress relief is required, the solution annually at about 1100 degrees Celsius can be used, although some strength is sacrificed. Overall, yield strength is mainly controlled by microstructure, while failure is often controlled by defects. As a result, LPBF 316L is particularly attractive for marine and chemical applications where corrosion resistance and long-term durability are critical. To summarize the practical recommendations, first, use processing parameters that provide sufficient energy for the full melting while avoiding excessive energy input that causes defects. Second, apply appropriate heat treatment to reduce residual stress and improve the microstructure stability. Finally, maintain good power quality and perform surface finishing to provide fatigue performance. By balancing these factors, LPBF 316L can achieve high strength, excellent corrosion resistance, and long surface life in demanding engineering applications. Here's my citation, and thank you for listening.